Hello everyone, my name is Yuzhou Feng. It's my great honor today to present our project SolarTrader, enabling distributed solar energy trading in the residential virtual power plants. This is a joint work with my lab mate Qi, my advisor Dr. Chen, and also our collaborator Dr. Rangaswan. This is the work of the Cyber Physical System Lab from the Florida International University. As we all know, distributed solar energy resources, as known as the DSER, are rapidly increasing these years. We can see from this graph. The yellow line shows that the solar PV module price dropped 4 times in the past decade. And the bar chart shows that solar PV deployment grew 18 times in the meanwhile. This kind of penetration has promoted utilities to balance the real-time supply and demands of the electricity in real-time proactively. To accommodate this solar penetration, recently there is a rising interest in using virtual power plants technique to mitigate the impact of the intermittent distributed solar energy resources. So VPP basically is a virtual aggregated of different energy resources, as you can see here in the graph, such as EVs, wind farms, rooftop solar arrays, and community sharing solar arrays. And this gave us a bigger vision for the entire energy market. It will benefit both user and the market to maximum their revenue potentially by using the renewable energy trading. However, the existing solar trading process has efficiency issues. First, existing energy trading approaches require trusted third party to play the role of an online middleman, which in order to supervise the trading process. And due to a lack of fair trading algorithms, some of them cannot ensure and guarantee the fair trading. And some of them do not allow users to trade their surplus solar energy independently and concurrently. All these issues create a barrier for the user to receive their maximum benefit. We observe from the existing works that enabling trading of surplus solar generated energy among the VPP DSER neighbors, it has the potential to provide the VPP users additional monetary benefits. It also mitigates the unfairness in long-term energy saving outcomes. So we can see these two graphs here, A and B. X-axis are 4 different VPP locations. We reviewed the 3 different recent energy trading approach, the pure sharing, first come first sharing, and round robin. As shown in graph A, we can see this algorithm indeed increased the monthly energy saving. And for the graph B, the y-axis is a Gini coefficient. We can see they can also mitigate the unfairness. But none of them can achieve both benefits simultaneously. So our insight is, can we design a new approach that receives this benefit at the same time? So our research problem is to find the minimum energy cost over time in the entire VPP environment. In the meanwhile, we want to ensure the fairness in the long-time trading process. To address this issue, we propose a new system, SolarTrader, that enables the unsupervised, distributed, and long-term fair solar energy trading in the residential VPPs. In particular, our design of the SolarTrader leverages the multiple agent deep reinforced learning process. For example, as shown in this graph, different DSER users can be abstracted as an agent. Our idea is the collaborative environment can enable the concurrent and distributed energy trading among all the agents in a VPP. We have 4 steps to build our system. I will walk through each step in the following slide. First one, we describe the agent with the following 6 aspects: energy consumption, net load demand, solar generation, battery capacity level, aggregated grid energy consumption, and the fairness. which is quantified by the Gini coefficient. These are the information we collected to modeling the agent state. Next, we design the action set for each agent. The agent can perform only one of these actions at a time. As you can see here, the agent can consume solar generated energy. They can charge the battery. They can also discharge the battery for either meeting their local demand or trade with their neighbors. With trading the energy, they either borrow from or lend to a neighbor. If they still have extra energy left, they can feed back to the grid. And of course, if they don't have enough energy, they will draw the energy from the grid. Basically, these are the actions that agents can perform in the solar trading system. So once the agent states and the action sets are well developed, next, we want all agents to learn a model to work together and help the user reach maximum benefit. So how do we do this? Basically, it depends on this reward function. I'm not going to get into the details of these parameters, but I will show you the idea. We consider 3 parts for our reward function. First part is the energy cost. As shown in the second equation, we consider the energy draw from the grid, the energy traded with your neighbors, and the surplus energy feedback to the grid. On top of that, we consider the VPP level energy consumption variance for better grid management performance, in particular for the net grid forecasting. What's more, we also consider the fairness by calculating the Gini coefficient. But we all know there are always exceptions. Some agents probably perform the wrong behavior, so we definitely want the agent to perform normally during the training process. So we enforce a penalty model, which encourages the agent when it remains in reasonable boundaries, and give a penalty when it acts abnormally. Since we have designed reward and penalty functions, last step we want to do is to train the optimized learning policy. We basically review the most recent training algorithms, and we do a little bit of benchmarking. So for graph A, y-axis is the training time, and the x-axis is the different algorithms. We can see different algorithms have different training time. And the y-axis of the graph B is the reward mean, and the x-axis is the training episodes. It shows the trend of the training reward mean are also different during the training process. Considering both training time and the reward mean, we select the policy gradings as the SolarTrader policy training approach. To implement our SolarTrader system, we implement both the simulation and the prototype with Python and several most popular open source frameworks. We use Panda for the data pre-processing, OS Brain for our multi-agent communication system, and we also use the scikit-learn and the PyCUDA for our deep reinforcement learning. So to evaluate our SolarTrader system, we prepare multiple data sets, such as Pecan Street, which is a data collection company. We also get some data from the eGarch, and we also collaborate with the UMass SmartStar dataset. For our evaluation matrix, we use the Gini coefficient to evaluate the fairness, which is the lower the better. 0 means perfect equality, and 1 means the worst equality. Then we want to show several proofs that SolarTrader has better performance than other approaches. So first, we evaluate the reduction of the energy consumption in the aggregate level. As we can see in the graph, for hours in a day showing on the x-axis, and SolarTrader has the overall lowest price consumption as shown on the y-axis. It also flats the average energy consumption for each hour. SolarTrader is also the best performing approach every day in the year, and it results in a significant average reduction in the aggregated net energy drawn from the grid across 4 different VPPs. Next, we examine SolarTrader regarding saving the monthly electricity bills. Interestingly, we can see from our 4 different VPPs, the SolarTrader is always the best performing approach, achieving over 100% average saving on users' bills. We also consider SolarTrader performance for long-term trading fairness. The y-axis in this graph is the Gini coefficient to evaluate the fairness. We can see the SolarTrader yields the best fairness of solar energy trading for most of the locations. We also evaluate SolarTrader's performance when the size of the agents is increasing, basically the scalable performance. We can see from graph A, when the number of the agent is increasing in the x-axis, SolarTrader results a higher monthly energy saving. And we can see from the graph B, SolarTrader shows a smaller GC value when the more agents are in the VPP, which means the more users in the SolarTrader system, the more fairness we can achieve. Eventually, SolarTrader can also improve the grid operation performance, in particular for the net grid forecasting. As we can see from the graph, the y-axis is the net energy drawn from the grid. X-axis are the months. The top part is the largest remaining first sharing, which is the most efficient current work. Compared to it, we can see in the lower graph, our proposed SolarTrader have more stable net grid demand profiling. We perform a PF test. We prove that SolarTrader enable VPP has a better performance respect to net demand forecasting. The more details about our evaluation are in our paper. In conclusion, we present a new system that enables unsupervised, distributed, and long-term fair solar energy trading in the residential VPPs. SolarTrader leverages the new multi-agent deep reinforced learning approach that enables the P2P and distributed solar energy trading among these different DSERs to ensure both VPP user and the grid to maximum benefit simultaneously. We also have multiple things we want to do in the future. We plan to deploy a prototype of SolarTrader into community solar sharing systems to further explore the benefits of solar energy trading. We also plan to design new policies to integrate more different kinds of agents to our trading system, such as EVs, utility batteries, and wind farms. We also plan to integrate SolarTrader with the most recent solar generation forecasting model to enable day-ahead trading. So that's all my presentation. The source code of our work is released on this link. If you have any question, please let us know. Thank you.